The drifting continents. Alfred Wegener stood in the crisp air of 1912, holding a map that defied geological consensus. He was not a radical by nature, but a meteorologist with an obsessive eye for detail. In his office at the University of Marburg, he traced the jagged coastline of South America against Africa's bulge. It looked less like coincidence and more like a torn photograph. For years, geologists had insisted continents were fixed pillars of the Earth, immovable since creation. Wegener proposed they drifted, carried by forces unknown to science. His evidence was compelling yet dismissed as poetic fantasy. Fossils of Mesosaurus found on both sides of the Atlantic suggested a land bridge that never existed. Glacial striations in tropical regions hinted at past climates that contradicted current models. Colleagues mocked him, calling his theory absurd, yet the data persisted. He gathered pollen samples from polar regions and ice core records that painted a picture of a shifting world. Despite ridicule, he continued his expeditions to Greenland, seeking proof of movement. The scientific community remained steadfastly opposed, viewing continental drift as heresy against established dogma. Wegener died in 1930 during an expedition, his theory unproven and largely ignored. But the pieces of the puzzle remained scattered, waiting for someone else to assemble them into a coherent truth. Pangaea. Decades after Wegener's death, new technologies emerged that would vindicate his controversial hypothesis. In the 1950s and 60s, paleomagnetism allowed scientists to measure the magnetic orientation of rocks. They discovered that rocks formed at different latitudes showed varying magnetic alignments, implying continents had moved relative to the poles. Simultaneously, sonar mapping revealed mid-ocean ridges where new crust was forming. Harry Hess proposed seafloor spreading, suggesting magma rose at ridges and pushed plates apart. This provided the missing mechanism Wegener had lacked. Alfred Wegener's fragmented evidence suddenly snapped into a cohesive theory: plate tectonics. Fossils matched across oceans not because of land bridges, but because those lands were once joined as Pangaea. Volcanic arcs and earthquake zones aligned perfectly with plate boundaries. The scientific community, previously resistant, rapidly accepted the paradigm shift. Today, GPS technology confirms that continents continue to drift centimeters each year. What began as a ridiculed idea by a meteorologist is now the foundational framework of geology, explaining earthquakes, volcanoes, and mountain-building processes globally. Wegener's legacy. Alfred Wegener's journey from outcast to celebrated pioneer illustrates the non-linear path of scientific truth. Initially dismissed as an amateur meteorologist meddling in geology, he faced personal tragedy with his wife's death and professional isolation. His expeditions to Greenland were fraught with danger, ending in his fatal accident in 1930. For decades, his theory lay dormant, criticized for lacking a driving mechanism. It wasn't until the 1960s, with advancements in marine geology and paleomagnetism, that pieces fell into place. Seafloor spreading provided the engine for continental drift. This transition highlights how science self-corrects over time through technological progress and open-mindedness. Today, plate tectonics is uncontroversial, explaining natural disasters and resource distribution. Wegener's story teaches resilience against peer pressure and the importance of empirical evidence over authority. His legacy extends beyond geology. It serves as a metaphor for any field where innovation challenges tradition. Whether in medicine, physics, or social sciences, new ideas often face resistance before acceptance. Recognizing this pattern helps us remain vigilant against dogma, ensuring that rejected theories aren't discarded prematurely, but evaluated fairly when sufficient proof emerges. Invisible killers. Ignaz Semmelweis worked in the chaotic wards of Vienna General Hospital in the mid-1840s. The maternity clinic was divided into two sections, one staffed by doctors and medical students, the other by midwives. The mortality rate from puerperal fever in the doctor's ward was horrifyingly high, often exceeding 10%, while the midwives' ward had rates below 2%. Semmelweis noticed something peculiar. Doctors came directly from dissecting corpses to deliver babies. Midwives did not perform autopsies. He hypothesized that cadaverous particles were being transmitted on hands and instruments. His proposal was simple yet radical: wash hands with chlorinated lime solution before examinations. Within months, mortality rates plummeted dramatically. However, the medical establishment reacted with fury. To suggest that respected physicians were killing their patients through negligence was an insult to their honor. They rejected his findings, claiming miasmas or moral failings caused the deaths. Semmelweis became increasingly agitated, writing bitter letters accusing colleagues of murder. His behavior grew erratic, leading to his confinement in an asylum where he died shortly after admission. It took decades for Louis Pasteur and Robert Koch to validate germ theory, proving Semmelweis right posthumously. Semmelweis reflex. The term Semmelweis reflex describes the instinctive rejection of new knowledge because it contradicts established norms. Ignaz Semmelweis faced this violently. After discovering hand-washing reduced childbed fever, he published his findings in Hungarian and German journals. European medical elites ignored him or mocked his lack of formal credentials and abrasive personality. He accused doctors of being murderers, burning bridges with potential allies. His mental health deteriorated, leading to institutionalization. Ironically, while he suffered, other hospitals adopting hygiene practices saw mortality drop without knowing why. It took Joseph Lister's introduction of antiseptic surgery using carbolic acid years later to gain acceptance for microbial transmission. Pasteur's experiments finally explained why washing worked. The tragedy underscores that scientific progress isn't just about discovery, it's about communication and overcoming social inertia. Semmelweis died unrecognized, but his simple intervention saved millions. Today, hand hygiene is standard practice globally. His story reminds us that truth often arrives uninvited, wearing uncomfortable clothes, demanding we question cherished beliefs before accepting evidence-based reality. Mars Canals. Percival Lowell built an observatory in Flagstaff, Arizona, in 1894, driven by a singular obsession: life on Mars. Using powerful telescopes, he claimed to see a vast network of straight lines crisscrossing the Martian surface. He called them canals, arguing they were artificial structures built by intelligent beings to transport water from polar ice caps to arid equatorial regions. This idea captivated the public imagination, inspiring novels and films. Lowell spent years mapping these features, publishing detailed charts that seemed irrefutable to laymen. Astronomers like Giovanni Schiaparelli had previously noted canali, which Lowell mistranslated as artificial channels rather than natural grooves. The scientific community remained skeptical but intrigued. Lowell's reputation lent weight to his claims, yet independent observers often failed to replicate his sightings. As telescope technology improved, higher-resolution images revealed no such linear structures. Instead, the canals appeared to be optical illusions created by the human brain connecting random dots. By the time Mariner 4 flew past Mars in 1965, sending back stark, cratered images devoid of waterways, Lowell's dream was shattered. His legacy remains a cautionary tale about confirmation bias. Heliocentrism. Nicolaus Copernicus lived in a world where the Church taught that Earth stood still at the center of the universe. For centuries, this geocentric model explained celestial movements adequately enough for navigation and agriculture. But calculations grew complex, requiring intricate epicycles to account for planetary retrograde motion. Copernicus, a canon and mathematician, sought simplicity. He proposed that the Sun, not Earth, was stationary at the center, with planets orbiting around it. This heliocentric model elegantly resolved astronomical anomalies without convoluted corrections. However, challenging Aristotelian physics and scripture was dangerous. When his book De Revolutionibus Orbium Coelestium was published in 1543, he was on his deathbed. Even then, the reaction was hostile. Galileo later defended these ideas using telescopic observations, facing trial and house arrest. The Catholic Church banned heliocentric texts for nearly 200 years. It took Isaac Newton's laws of gravity to provide the physical mechanism Copernicus lacked. Yet the shift from Earth-centered to Sun-centered cosmos fundamentally altered humanity's place in existence, proving that intuitive truth often contradicts observable reality. A viral culprit. In the early 1980s, a mysterious illness struck young gay men in Los Angeles and New York. It caused rare cancers and opportunistic infections, devastating immune systems. Many doctors suspected environmental toxins or recreational drug use. Robert Gallo, a prominent virologist, believed a retrovirus was responsible. He isolated HTLV-3, later identified as HIV, claiming it caused AIDS. However, Luc Montagnier in France had already discovered a similar virus earlier. A bitter priority dispute ensued between American and French scientists. Initially, some researchers doubted a virus could cause such rapid immunodeficiency. Others argued lifestyle factors were to blame. Clinical trials showed antiretroviral drugs suppressed viral load and improved patient health, confirming the causal link. Despite initial skepticism and political delays in funding research, the identification of HIV revolutionized medicine. It led to testing protocols, safer sex education, and life-saving treatments. The controversy highlighted how scientific prestige can cloud judgment, but ultimately, empirical data prevailed. Today, HIV management allows infected individuals to live near normal lifespans, transforming a death sentence into a chronic condition through rigorous scientific validation. The expanding cosmos? Albert Einstein developed general relativity in 1915, describing gravity as the curvature of space-time. His equations suggested the universe should either expand or contract. A static universe was unstable. Yet, believing the cosmos eternal, Einstein added a cosmological constant to force stability. Edwin Hubble, observing distant galaxies through the Hooker telescope, found their light shifted toward red, indicating they were moving away from us. The farther the galaxy, the faster it receded. This expansion implied the universe began from a singular point, the Big Bang. Einstein later called his cosmological constant his biggest blunder. Georges Lemaitre, a Belgian priest and physicist, had independently proposed an expanding universe based on similar mathematics. Initially dismissed by Einstein, who famously said, "Your calculations are correct, but your physics is abominable," Lemaitre's theory gained traction as more evidence accumulated. Cosmic microwave background radiation discovered in 1964 provided definitive proof of the early hot state. The shift from a static to an evolving universe changed our understanding of time, origin, and destiny, illustrating how even geniuses can resist paradigm-shifting truths until data becomes undeniable. Viking landers. In 1976, NASA landed 2 Viking probes on Mars, tasked with searching for life. The landers carried 3 biological experiments designed to detect metabolic activity in soil samples. One experiment injected nutrient broth into Martian soil and detected gas release, suggesting microbial metabolism. Scientists were excited. Perhaps life existed after all. However, subsequent chemical tests showed the soil was highly reactive due to perchlorates, which could mimic biological reactions when heated or exposed to water. The consensus shifted. No definitive proof of life was found. Yet recent rovers like Curiosity have discovered organic molecules and seasonal methane fluctuations, reigniting interest. Methane can be produced by geological processes or biology. While Viking results remain ambiguous, they weren't wrong to look, they lacked context. Modern analysis suggests past conditions might have supported life. The initial disappointment taught scientists humility. We assumed Earth-like biology would behave predictably. Now astrobiologists consider extremophiles and alternative biochemistries. The search continues, driven by the possibility that Viking's positive result was a false negative caused by unknown chemistry, waiting for better tools to confirm if we are alone.